Hi everyone, welcome back. In this section we're going to be talking about finding the powers and roots of complex numbers. So just recall that we had two ways to represent a complex number. So we have the form a plus bi, and we also have the form r cosine theta plus I sine theta. So we saw in the previous section that if I take two complex numbers, say z1, which is equal to r1 cosine theta plus I sine theta, theta 1, and z2, which is r2 cosine theta 2 plus I sine theta 2, that z1 times z2 is going to equal r1 times r2 cosine of theta 1 plus theta 2 plus I sine theta 1 plus theta 2. So we're just to deal with a exponential situation. All we're going to do is kind of extend this definition. So what if I say z1 is equal to z2, where both of them are just r times cosine theta plus I sine theta. So if I do then, if I do z1 times z2, that's just really like, if I call that then just that number just z, I'd have z squared. So if they're exactly the same, I'm going to have r1 and r2 are the same, so I get r squared there. Theta 1 and theta 2 are the same, so I'm just going to get cosine of 2 theta there. And same thing here, if theta 1 and theta 2 are the same, I'm just going to end up with sine 2 theta there. So then if I wanted to say do z to the third, well, I would just have z times z squared, so that'd be r times r2, because now z squared is my second one, so my r2 or r squared is there, and I'll have cosine of theta plus 2 theta, right, because theta 2 is now so we have cosine of theta plus 2 theta, and then plus I sine theta plus 2 theta again. So when we simplify this down, we get r cubed cosine 3 theta plus I sine 3 theta. And at this point, we should start seeing a pattern, right? So what is the pattern that we should be seeing? The power on our complex number should match the power on our modulus and the coefficient on our argument. So let's write that out as a formula. So c to the n is equals r to the n times cosine n theta plus I sine n theta. And this formula has a name. It's called Demaurice Theorem. And it's named after the French mathematician that developed this. So let's do a quick example. So let's say we have the complex number z, which we know the trigonometric form for. It's 5 times cosine of 14 plus I times sine 14. And we're going to say, what we're going to do is we're going to find z to the 5th. Okay, so using that formula, I'm going to have r to the 5th, and then I'm going to have cosine of 5 times 14 plus I times sine of 5 times 14. And now we're just going to go to our calculator to get a decimal approximation for this. And we'll give our complex number here to 2 decimal places. So we're going to end up rounding. That's okay. So the first part, the real part, is going to be 5 to the 5th times cosine of 5 times 14. Before I do this, I'm just going to check that my calculator's in degree mode, which it is. So I'll do 5 to the 5th times cosine of 5 times 14. So that gives me 1068.81. And then we'll do the same thing for sine. So I'll just recall that last thing I typed in and turn that into a sine. So we get 2936.54. So I have then 1068.81 plus 2936.54i. And that's basically it for how we use that formula. So that should be pretty easy. Next up then is to deal with roots of complex numbers. So recall, if you will, that we had a formula for converting radicals into exponents. So if we have the nth root of some complex number written in trigonometric form, that's just going to be converting that into a fractional exponent. And then if we just apply Demaurice Theorem to this, that's going to give me the nth root of r times cosine of theta over n plus I sine theta over n. So this is our formula. But the problem is, this isn't quite it. It's actually a little bit more complicated, because if you remember, if we talk about what are the square roots of 4, well, you have 2 and you have -2. So we have to be a little bit more careful, because we want to be able to identify all the possible square roots for these complex numbers. So this formula we can actually extend, because we need things that are also going to be coterminal to those angles. So if we extend this, what we're going to get is cosine of theta plus 360k over n plus I sine theta plus 360k over n, where k is going to equal the number 0 up to n minus 1. Or we could express this in radian form. So again, we'll have the nth root of r times cosine of theta, but instead of 360k, we'll have 2 pi k over n plus I sine, and again, instead of 360k, we'll have 2 pi k over n. And again, k is going to be just the number 0 to n minus 1. So what we're saying here then is that the number of solutions is going to be the number of the same as the number of values we can express for k. So if k goes from 0 to n minus 1, that's n solutions or n values that we're going to have for any nth root. So let's look at an example or two here to kind of get the hang of this. Because while it's not a complicated idea, you know, like certainly doing a specific example kind of helps. So what if we want the cube root of 3 minus 2i? So the first thing that I'm going to do is I'm going to want to take my complex number, which is 3 minus 2i, and I want to convert this into trigonometric form. So to do that, I'm going to need a value for r, which is just going to be the square root of 3 squared plus negative 2 squared. So that's going to be the square root of 13. And then I need to find the argument here, now that I have the modulus. So I'm going to graph this complex number. So I'm going to go 3 over and 2 down. So there's my value. And what I want is this angle here, theta. So what I'm going to do is I'm going to start by finding this value alpha. And I note that theta is 360 minus that alpha. And alpha is just going to be tan inverse of the absolute value of the y component, or the imaginary part, over the x component, or the real part. So when I type this into my calculator, if I do tan inverse of, and I'm going to just do the absolute value in my head to give me tan inverse of 2/3. That gives me 33.69 degrees, approximately. And when I do this, then I get that this is I guess I thought I was going to be able to, do that in my head, and brain said, no, I'm not doing that for you right now. So I get 326.31. Okay. So we can say then z is the square root of 13 times cosine of 326.31 plus I sine 326.31. Great. So if I want the cube root of z, then I'm going to want the cube root of the square root of 13 times cosine of 326.31 plus 360k over 3 plus I times sine, I said 326 and I did not write it. 326.31 plus 360k over n. And then k is going to equal 0, 1, and 2. So again, we start at 0, and we do 1, 2, and we go up to n minus 1. So the n in this case was that we're doing a cube root. So starting at 0, we count up to n minus 1. So if we do that, we get 2 as our maximum value for k. So what I'm going to do now is I'm going to evaluate this for these different values here. And I'm just going to use my calculator to do this because, well, it's just kind of a lot of calculation, and I can't do these sines and cosines in my head. That's just crazy talk. All right, so math, and then to get my cube root, I'm going to go down to command 4, and then cube root of square root 13. Some of you might have recognized that that's just a 6th root. You could do that too. No big deal. And then I'm going to do times the cosine of, and then I'm going to pick the fraction command. So I did alpha and y equals to get that fraction command. So I have 326.31 times plus 360 times 0 over 3. Again, I'm plugging in that first value of k right now. So our final answer here, cube root of z, is going to be negative 0.493 plus, and then I just need to do the same thing with sines there. So I'm going to just recall that last thing by pressing second and the enter button, and just go back and turn that cosine into a sine. And I have plus 1.452i. So we've got our solution when k is equal to 0. Now we're going to do the same thing when k is equal to 1. So I'm going to just press second and enter twice to get my cosine one back up. And I'm just going to go back and change this 0 to a 1. And there's my next real part. So that would be negative 1.011. And then I'll press second and enter. And I just need to change that cosine into a sine. And there's my imaginary part. So I guess instead of a plus sign here, I'm going to write a subtraction symbol since that's negative. 153i. And then my third one, so I'm going to do the same thing. I'm just going to press second and enter twice to get back my cosine. And then I'm going to change that 1 into a 2 now. So there's 1.504. It's my real part. And then I'll press second and enter. And go back and change that into a sine. Press enter. So I have minus 0.299i. So those are my 3 solutions. So let's do that one more time. So I'll do that one more time with a different problem. Let's say we want to find the 4th root of 16. So if I want all of the 4th roots of 16, well, first thing I have to do is I have to rewrite 16 as a complex number. So that's just 16 plus 0i. So the r there is going to just be the square root of 16 squared plus 0 squared, which is obviously just 16. And then to find the argument, well, if I plot 16, 0, that's 16 over and 0 up. So there it's easy to see that theta is 0 degrees. So we can say 16 is equal to 16 times cosine 0 plus I sine 0. Okay. So then if I want the 4th root of 16, well, that's going to be the 4th root of 16 times cosine of 0 plus 360k over 4 plus I sine 0 plus 360k over 4, where k is going to go from 0, 1, 2 to 3. And now I'm just going to do the same thing I did before on my calculator. So we have the 4th root of 16 is going to equal. So do this just like I did before. So to get a 4th root, I'm going to press the math button and go down to option 5. And I guess I probably should have put the 4 first because now I have to backtrack here and change that, but that's not a big deal. 4th root of 16, and some of you might have recognized that's 2 right away, and that's fine. You could have just done that in your head. If you didn't see that right away, that's okay, not a big deal. You can always just ask your calculator to do it. And we'll set this up just like we did before. So we have that one. So if I do that, I get 2. And then if I change this now to sine, I get 0. So we have this is equal to 2 plus 0i, or just 2. Go back and do the same thing. So I'll press second and enter twice to get the cosine back up there. And then I'll just change that 360 times 0 to 360 times 1. There I get a 0. Press second and enter. Go back and change the cosine into a sine. And there I get 2. There I get 2i. And press second and enter twice to get the cosine back up. And then we'll just go in there and edit that 1 and change it to a 2. It gives me a -2. And when I go back and I do the same thing here for change that cosine to a sine, I get 0. So I have -2 plus 0i. Well, that's just -2. And then my last one, so press second and enter twice to get my cosine to come back up, and then I'll change that 2 to a 3. You get 0, press second and enter, and then go change that cosine to a sine. Press enter, gives me -2. So my 4 solutions then are those. And that's kind of all there is to it. So we're just kind of using those formulas each time. Shouldn't be too bad. For your homework in this chapter, I need you guys to do 65 through 120. But the good news is it shouldn't be too bad. None of these should have been that difficult. A lot of them are just like calculator punching, so shouldn't be so bad. All right, good luck, and we'll see you next time.